Hello, everyone. GM, morning, good afternoon, good evening, good night. Welcome, everyone, for lesson 19. Keeping on exploring those branches of the knowledge around the EVM, around programming with Solidity, building smart contracts. Today, we're going to see another detail that can be overlooked, another uh, uh, another consequence of using decentralized computing, decentralized systems. We saw on one day that we have the complexities about gas costs, depending on how we implement the same thing, could cost more or less. It could be more secure, less secure, having problems. Yesterday, we saw that we have a limit on the amount of operation that we can do per block because of the decentralized architecture of those blockchains. Today, we're going to see that we have a problem about the randomness, something that is so simple in all the programming languages, in computation systems. When we go for blockchains, especially the EVM or similar ones, it's very difficult to get randomness there, any kind of randomness, because of the deterministic nature of these blockchains. Okay, so we're going to see that very slowly, very in detail, the problem happening, like we did yesterday for half an hour or so. We're going to see this problem. We're going to understand why it happens, why it's unavoidable, and then we're going to see some solutions for this. Okay. Before we begin, let me just verify one little thing. Yesterday lesson was about what? If you can summarize yesterday's lesson in one word or two words, just to make sure that we got this correct. Yesterday's lesson was about, and if you summarize it with a
Gas optimization, reduce the gas, reduce the gas in for block, gas optimization.
for gas, yes, it was dealing with gas limits, correct, Johnson? Correct. Gas limits and why running loops on the blockchain is hard. Yes, Arda, very good, very good. I'm good with y'all. Okay? There are some people that say, "Oh, lesson 18, the lesson about sorting," and I'm like, "What?" No, yesterday's lesson wasn't about sorting. Okay, sorting was just an example because you should not sort on chain. Everyone knows that. So if you go telling people that you learn sorting on chain, it becomes like some sort of joke. Okay, we just wanted to get that clear. Yesterday's lesson was about gas limits, like Johnson answered, like Arda answered, like Nathan answered. That's correct. We use it sorting as an example, a visual example. But we should not sort on chain. Okay, so lesson 18 was not about sorting, it was about gas limits. We saw the problem happening and then we solved it. Today we're going to speak about randomness. Okay. Have you used randomness in some other code that you did in the past? Maybe some game, some script, generate a random number on JavaScript, on C, Java, blah, blah, blah. It is very simple to generate a random number with those programming languages, right? It's not true randomness. There is this whole discussion that the source of the entropy could be measured if you use a bad random number generation for security purposes, like generating hashes, keys. If you use it for generating like a seed or generating like a result of a lottery, it can be exploited if the randomness is not that good. Okay. So, for example, there are some data centers that have those lava lamps to capture entropy from there and use that as a source of randomness, the movement of the mouse and all. Yes, there is this whole discussion about having true randomness. Today's lesson is not about that. It's not about perfecting randomness generation for security reasons. Today's lesson is just having any random number, any simple random number like math.random, like we have in all the programming languages, which is so simple to do. Let me show you in a browser. Let me pick any browser tab. Let me open the console. Let me go here for the code, and let me pick this math.random method. This is a random number. See, I guess it's too small. Let me paste here in the chat. So this is something that you can do very easily in many programming languages. It's true randomness. It's perfect randomness. No, it's not like that. Today's lesson is not about this discussion. It's about having any kind of randomness. Now, I want to play a game in my smart contract. Tomorrow we're going to do a challenge about a lottery. A lottery should have a random result, right? So having this kind of random results inside blockchains, inside smart contracts, is very difficult, almost impossible unless we tweak it around like we did yesterday. Let me show that for you. Let me create a new project. I guess we can copy this gas limit project that we had. Copy all of these files and let me create a new one for randomness. Let me paste everything here. Opening terminal. Nothing new here, okay, people? I've been doing that for 20 lessons now, not in the first week, but let's say for more than a dozen lessons, okay? So npm, let me open that on the cursor already. Then I'm going to do npm install, get that folder started. And we're going to create a project here for us to study this randomness. Okay, let me do npm install, and let me organize this project with some folders. I'm going to need a folder for contracts, and another folder for scripts. Contracts and scripts. And let's say I want to do a lottery, I want to do a game, I want to do something that requires a random number generation, an NFT minting or something like that. And I need to call that smart contract, okay? I'm using VM, copied from yesterday's lesson where we used VM. On Monday, we used Ethers. Okay, we're not using Ethers this week. Next week also we are going to use Ethers just in one lesson, the upgradability. So for now, return to VM. Okay, you might have the recordings for Monday's lessons already in the Discord. It took a while to post, but finally we have there. You can watch that in the weekend or something like this if you miss it. But for today, using VM normally. And I want to create a contract, like my game or something like that. You don't need to create. I'm just going to use that for explaining. Like my game dot solve, and somewhere here inside my game, I want to have that project. I guess I'll need to restart my course in a while. Somewhere inside my game, I want to have a function that's going to use a random number generation. Pragma, solidity, my game. Okay, that's good. And then I'll have a function like play battle with something like this. Whatever cursor is going. Let me disable cursor here. Chill, my friend. You're too excited with this game. Disable. Okay. So play battle, public, whatever. And here I'm going to need a random function. So like the winner or the result of this battle is something that requires math.random, something like this, right? Yeah, my installation finished here. I'll have to restart cursor in a while, but don't worry. Just follow the explanation. Somewhere inside my smart contract, I need to have this math.random to determine the outcome of this battle or display or whatever that is happening. You're following the idea, right? But even if I had some way to implement that, spoiler, there is no way. But even if someone invented a way to get some sort of randomness, some source from inside the EVM, from a byte that is somewhere that can be 0 or 1 as a source of entropy, and then would calculate this randomness there. Even though if we had some way to do randomness inside the EVM, I would have a huge problem. We say that something is random when we cannot measure the outcome, right? For example, we say that a dice, throw a coin, throw a toss coin, could be head or tails. We say that it's random because we cannot measure the outcomes, right? If we had all of the variables, for example, the wind speed, the angular velocity of the coin, the momentum, the density of the air, the viscosity of the air, the roughness of the coin surface, the roughness of the surface where it's going to land, all the vectors. If we had all of this information inside the computational model, we could calculate deterministically what is the outcome of that throw. If we bet $1 billion in a coin toss, it would be interesting to measure all of those things to know if it is head or tails, right? But we don't. When we throw a coin, we just move the finger with some string. We don't know anything, any of those variables, right? So this is why we deem the result random. But we know that there are some physics, some deterministic effects influencing that outcome that we cannot measure. This is the reality of randomness, how the entropy would work. When we try to emulate that in the blockchain, something that we don't control the output, something that we don't know. Imagine that we have this kind of function here, math.random, and imagine we use that inside a transaction. For example, let me pick any random transaction on the blockchain. This transaction here. And imagine this is a math.random transaction. It was confirmed. Let me pick a most recent transaction. 8 seconds ago. Good. So this transaction was confirmed with one block confirmation. And we have the state change. Imagine this is smart contract. Play battle is going to have an outcome. Who's the winner? Who's the loser? Based in this random throw. Let's say it's a coin toss. And it would have some state changes like this, right? I would have a state before and a state after. And someone computed that and we had success. Then when I have the second block confirmation, now we have 4 block confirmation in that in that transaction. So when we have the second block confirmation, someone is going to run that math.random again and is going to determine the outcome. Let's say the first block confirmations determine that the player A is winner. Now the second block confirmation is determined that the player B is the winner. And then the third block confirmation is determined that the player C is the winner. And now the fourth block confirmation is determined that the player B is the winner again. So how to believe, how to have consensus over the result of a random operation, if it is random, if it every time that someone computes that, they would get a different value. Remember, we cannot pick the first one because we don't know who was the first. We need to have a decentralized way of checking that. So anyone could have computed that first. The first one could even have lied, so you need to verify it again, right? So imagine that if we had a way to have this math that random here, how would we have consensus? What do you think? Do you see the problem? Yes, Dante.
Yeah,
Give me your
Is
takes.
it a problem? Because I thought I had an answer.
Yeah, no, yeah. And this is the problem. We would never have consensus. Sometimes people will agree that the player A is the winner, and then eventually, based on luck, the player B could be the winner. And then eventually, based on luck, the player C is the winner. And we never know the winner. It could be changing over time based on just how the randomness work, right? So you never know who was the winner. You see this problem? Kind of paradox, yes. Arda, let's me. Tell me, share me your thoughts on this.
Well, you're going to read the randomness from some sort of an oracle that was once computed, and it better have proofs. So that's what's called a verifiable random function.
Yeah, so we're going to see those techniques. But first, before I explain those techniques, I need to explain why we can't do it natively. Why we can't call a random function. And this is something I mentioned in the first lessons. People think that Solidity is limited, that Solidity was badly designed because it don't have any random function on it. It doesn't have API calls. It has guess limits. The whole idea of this bootcamp is demonstrating why actually those things are not the flaw of Solidity or the EVM. This is by design. This is by architecture. Okay, so it's very important that we have time to do this. So before going to the solutions, I'm explaining why it's not possible that we have a function in Solidity, as we have in some other systems, to generate a random number. It's not possible. It's definitely not compatible with the architecture of the blockchain. That needs to be deterministic. We need to have a deterministic result so that we can have a consensus. So it's not possible to do this math random. My game cannot be built. Okay. Is that clear for everyone? Good. So how to do randomness on chain? You don't. Okay. I hope you enjoyed today's lesson. Okay, see you tomorrow. Just kidding. No, people. We have workarounds for that. Okay. I'm going to explain those workarounds now. Now that we understood the intrinsic problem of randomness, it needs to be deterministic. You need to come from a determined source. I'm going to show some ways, the good, the bad, and the ugly ways for having randomness on chain. Okay, how to work around, how to solve this limitation, this intrinsic limitation because of the architecture of blockchains. Okay, and we're going to guide ourselves by this article. Okay, the motivation of randomness. You might have seen some smart contracts that use random numbers. For example, minting NFTs. Then you have a random NFT minted, or battling like Axie Infinity, or those games where you battle, or CryptoKitties when you want to breed a new NFT. You use some sort of randomness. So they are using some of these sources of randomness, and we have randomness sources like block hash and timestamp, where you would have some information of the block as a source of randomness, or some information of the transaction like timestamp or something like that, or message send or whatever as a source of randomness. You can have oracles. We saw oracle partners like last Thursday, Chainlink and Tello, how you can have people from outside of the blockchain give you randomness. Or you can have a collaborative pseudo-random number generation, for example, RunDAO, that is an on-chain method to generate randomness that wouldn't rely on external sources. Okay, we're going to see the three of those today. The first is very simple, but is very flawed too. The timestamp of a block, the hash of a block, all the information of a block on the transaction, they can be manipulated by miners and by validators. Okay. So the first kind of pseudo random number generation that we're going to see is kind of a weak method. It can be exploited. So if you put something that is worthy enough, like worth $100 or more, $1,000 or more, you have incentives enough that someone would go there and manipulate that result to win that game or to mint that rare NFT. Okay, it has happened in the past. People could snipe good rare NFTs and spike the price of minting, exploit with MAV just by manipulating the hash timestamp of a mint, because it would be deterministic enough for them to know that this result was like that. And then if the NFT is worth $1 million, oh my God, you have incentives enough for trying to exploit this. So it's simple. It is easy to implement, but it's also dangerous. If you're doing like a fun game without much of a financial without so many financial implications on it, like a fun game for you to play with your friends or your community, the assets are worth like $1, $10 each. You can use this kind of randomness. It's harmless. The worst case scenario, someone's going to hack for $10. If they go that way for hacking $10, they're really hungry or desperate, so let them be, maybe, because it is something that it's a hack that would an exploit that would consume a lot of computational resources. Eventually would not win a block reward. So it's not worth for you to do this kind of exploits if it's worth like $10 or so. The first randomness is limited. I'm going to show how to do. It's quite easy. We can pull it off in like 10 or 15 minutes maximum. Okay. Arda, you have a question here?
Not a question, but a comment, if you allow me.
Yes.
So the catch is, if somebody can guess your randomness while you're signing anything, they can recover your private key. So you have to be very careful on chain while using randomness.
Arda, you were speaking about signing transactions with
I mean, if whenever you use your private key with some sort of randomness, there are cryptographic techniques where I can recover your private key if I can know what your randomness is. So the whole problem is, if randomness can be manipulated, then everything goes bad.
Okay. In this situation here, we are speaking about getting random numbers inside smart contracts. So for example, this function random is going to return a random number from the block hash, like this example that we have here. So this is not going to compromise your signature, for example, your private key when signing this transaction. This is just about this smart contract, okay? There's nothing to be compromised on the signature part here, okay? But it's true, depending on what you want to do in other places, it can be very dangerous. But in this exercise that we have in this smart contract for today's lesson, it is just about random number generation inside a smart contract. So there is no way to go back from this to your private key here.
Yeah, no. What I was saying is, if you're writing your some sort of signing operation using some sort of randomness, the default signing operations on chains are not that bad, because they're actually using verifiable sources of randomness, that the random number was generated properly. So they're okay. But if you're writing your signature function on your own for some reason, which you might want to do, it's not that off the topic, then you have to use a decent source of randomness. Otherwise, you lose your private key, and which means you lose everything.
Okay, that's a good call out. Yes, we are going to even speak about signing. The discussion here, I guess, I could be broadened up a bit. Do never reinvent the wheel when doing signatures. Okay, always use the recommended protocols and techniques, especially when dealing with money, like signing a blockchain transaction. And I'm going to show these packages, how to implement them and all. VM would implement it, Ethers would implement it. So tweaking those is not a good idea. Good call out, Arda. I see some junior devs going that path. Oh no, I'm going to do a random number generation for this lottery by myself, and then they get hacked very soon. This is a very important subject. But today, speaking about smart contracts, it is more easy. But the scope is more contained here. So don't worry that much on the private key part. So let's create that smart contract, not quite random.solve. Let me restart my VS Code add-ons so I don't have VS Code no cursor. I keep calling the name of the X. I guess cursor would get jealous at some point. Okay, let me restart it just so that it picks things correctly. And I'm going to create this contract called not quite random. We're going to say that we're going to have randomness, but not it's not a very good randomness. Okay, it is a determined randomness where we can get information from the block hash. For example, I can pick the block hash of the last block. I cannot get the block hash of the current block. It's not calculated yet. I would need to go to the future, get the block hash, and then using the past, but then that would change the hash of the block, and then I would need to go to the future again and go back and forth, and that would create a paradox in time travel. It's not a good idea to do that. So we always pick the last block, and this last block has been there for a few seconds. Everyone knows the hash of the last block because it's public, is there in the blockchain. So it's very quick, very easily to quickly calculate this random number and front run that smart contract. Okay, it's not a very good randomness number. But again, if it's something funny for you to play with your friends in a small game, not much money involved, nothing that would compromise your private key or anything like that. It's just a small, quick game where you're going to get a random number. You can implement this like that. Get randomness from a block hash. I can pick the last block hash like this, translate that for a number, and return. This would solve. Okay. Instead of return, I can say that not quite random equals to that. And just a suggestion for readability, uint is an alias for uint 256. It's good to explicitly say uint 256 all the time because then it gets more readable. I know it's 3 characters more verbose, more stuff in the code. Yes, the code gets a little longer, but it's more readable. Oh yes, a uint is a uint 256. That's good. Okay, so you don't depend on the alias. It is the same thing. Okay, for the bytecode, uint and uint 256 is the same thing, just that it's more readable. Okay, so this would be the implementation of the not quite random to get a random number. This will return a weird number, 0.0. No, it would be like 1, 2, 3, 4, 5, 6, 7, 6, 5, 4, 3, 1, 0, a very big number with a lot of random things because it's speaking the hash, the bytes of the hash, and then translating that to the number that would have the same bytes. Okay, so it's going to look weird, but it is a number that has been out there for 4 seconds or so, and it can be manipulated. Okay, so if that is a prize of $1 million, if this is odd or even, a miner could try and get 4, 5, 6, 7, 8 blocks until it gets a block that it likes, and then it is going to propose this block. Okay, nothing guarantees that the block that the miner proposed is the only block that it calculated, especially in proof of stake, where they have a time, they have those epochs, they have a window where they need to propose a block. So they could calculate 10 blocks, pick the best one. Oh, in this one I'm going to lose, in this one I'm going to lose, this one I'm going to lose, in this one I'm going to win. So I'm going to discard all of those other blocks that I produced. I'm going to pick this block that I won, and I'm going to submit that block to the blockchain. The block producer has this power. Okay, next week, we're going to speak about DeFi. We're going to see even more about that, like manipulating trades, order of transactions, and things like this. So first exercise is this. I'm going to create a script called getRandomNumber.ts. This script, getRandomNumber.ts. And then I'm going to paste this block of code. Okay. Nothing new in the structure of that contract and the container script. Nothing new in the structure of that script. We are defining a function and then calling it here. Okay. This function, I know I imported more stuff here, but this function is going to deploy the smart contract with VM, like we did a few times. It's going to create a public client, like we did a few times. It is going to get the random number by reading this smart contract, this deployed smart contract, and logging it. Okay. I'm forcing the blockchain to mine a block. This is something that we can do in the hard hat runtime environment. And you can ask it to mine a specific number of blocks at a given interval. I could even configure the timestamp between all of those mined blocks if I wanted. Okay, so I'm going to mine a block and then get a randomness again. Mine another block and get a randomness again. Okay, let me run this script. npx add hat run this get random number, and it's going to output something for me. So compile that smart contract. It's going to run that script, and then this is the result that I have. In the first block, that was the block hash, and this is the block number. Random number 854812 ending 161. And then the second one like this, like that. These numbers, they seem quite random, right? A lot of entropy packet here. Okay. So this is the first attempt. It's not a good random number, but it's usable. Do not put anything that is worth a lot of money here. Anything above $100 or $1,000 could be enough for attracting an exploiter to hack this or to try to get advantage of this. But if you're doing that just for fun, in a quick implementation, it's good enough. And usually when you're going to consume this this kind of random number, you are going to reduce it, for example, to a dice throw. Let's say you're playing Dungeons and Dragons on chain, and you throw a d20 or a d6, or you're throwing a coin, so you want to know if it was head or tail. So you would reduce the random number to some number that you can use in your smart contract. How would you do that? Any suggestions? Nothing about randomness itself, but just to exercise or critical thinking, would you have some suggestion on how to determine heads from this random number? I would love some suggestions here. I could do something like this. If get random number equals to 0. Heads equal to true. If get random number equals to 1, heads equal to false. If you get where I'm going, right? This is the kind of programming that can keep people employed for years. We could have a squad of 8 people working that full time to complete that random function, and it would take some decades to finish, right? Or we could do this suggestion from Ulatzmir. Heads, thanks a lot, Ulatzmir. Or actually, I could complain, you stole a lot of jobs, okay? I could be working for a few years on this, and just by efficiently calculating the remainder of that operation, you reduced my work for a few seconds. So you hurt the global economy by doing that, okay, Ulatzmir? Just kidding. This can work, okay? I'm going to pick the random number, and I'm going to get the modulus from the division of 2. If the remainder is 0, I can say that it heads. If the remainder is 1, I can say that it's tails. Okay. Good. Now you prove that there are equal numbers of heads and tails of odds and evens inside you win 256. Okay. If you like a mathematical challenge, can be quite easy, but that's not part of this bootcamp. Now we have a function, toss coin, that is going to return either heads or tails, and I can call it from this script. So I can log whether we had heads or tails based on this function. Okay. So if I have heads, if heads return as true here, I'm going to print heads. Otherwise, I'm going to print tails. I'm going to do that 5 times. So I'm going to pick the toss coin here, and I'm going to call it here on the line 84. Okay. Do you want to make some bets? Do you want to test your luck? Do you think that we're going to have more heads or more tails? Tails, right? Maybe you will calculate, oh, I reach 256. When you go from 0 to 2 at the power of 256 minus 1. So what is the probability of having heads? What's the probability of having tails? Okay, do this calculation. Okay, no one else is going to bet. Ryan is the only lucky student here today. Come on, people, just it's worth nothing. I'm not going to charge $10. Let me run that. Okay, Ryan cried on tails, Nathan on heads. Let's see how this goes. So we have head, tails, head, tail, heads. Yes, heads won. Nathan, you tested that before, right? Good point there, Arda. Okay, we got heads. Maybe the distributions of hash are biased towards a number or the other. That can be possible, okay? But I can roll again, no worries. I can do the best of 3, right? You see how this can be used for a fun experience, a fun game, but nothing that would include money, nothing that would include big money. It can be exploited, but it is generating this kind of behaviors. So a lot of people jump to this kind of implementation. Oh, I'm going to use that for determining my NFT role. I'm going to do that to determine my lottery, my auction periods, whatever. And this is a security problem. Okay, this can be exploited, and we're going to see even more of that in the lesson 24. Okay, on some tools that we're going to use for finding these kind of problems, okay? Any questions up to here before we start going deeper on all the methods of randomness? Raise your hand if you just stop the lesson, ask some questions. No, okay, so let's keep going. So there are some problems. Here are the explanations of these problems. It can be manipulated and all. I'm going to skip for now the oracles. I'm going to mention that at the end of today's lesson. I've explained oracles already. And this is kind of like cheating. Okay, if we can't get a random number on-chain, let's get it from off-chain. It solves the problems, yes. But also introduce the other problems, the problems that we saw last Thursday about the Oracle networks. Either you are trusting an Oracle decentralized Oracle network with some how do you say, at some extent you are limited by how much the network is incentivizing correct behavior. It's not 100% BFT. Okay, it could have faults and then the person is going to be slashed or something like that, okay? Or you need to wait for a dispute time for a claim to be resolved and then voted. That there are many different architectures of oracles that could provide a random number, but they all would carry the problems of oracles that we saw last Thursday. So I'm going to skip this one for now, and we're going to stop using the block hash or the block Simonson as random number, or relying only on that. We can combine those later, and we're going to start studying collaborative pseudo-random number generation, okay? Before we do that, I want to organize this script in a way that we can interact with it from a CLI, from doing comments, okay? This is something that could be very useful since lesson 8, but we had so many things to study at the time that they didn't want to bother you with this. Today I can show it. It takes like 5 minutes. We can use this function read line from Node whenever we are using scripts from the terminal and all, and use that for creating those CLIs, commands like, remember when you start hard hat and it gives you those options with JavaScript, TypeScript, blah, blah, blah. We can do something like that when we are programming our scripts with this read line functionality. And it's very easy. Let me show that for you. We can import readline from readline. I have it in this script already. Import everything as readline from readline. Here, you see. I'm importing everything from readline. You don't need to import it from Node readline. You can import it just from readline. It works in this script. I'm going to create this main function that is going to have a question from the read line. The read line is going to use the process standard input and output, the terminal, running that from the terminal, from the console. So it's going to use the console. And then I'm going to ask questions in the console. Like, imagine you're doing that for the ballot. You could ask a question, which proposal do you want to vote for? Or type the address of the person that you want to give votes for. So you could ask a question like this in a string, and then you would wait for an answer in the terminal, in the standard input here, the terminal, and then depending on the answer, you can do different things. Okay, so you don't need to have all of those separate scripts like we have here. I have two scripts here, block, two functions in the same script, block hash randomness and toss coin, right? So instead of changing this line 84 that I had here for doing different functions, I can have this main function here that is going to ask the user, the person calling that script, what operation you want to do, and depending on the option is going to divert me, is going to guide me for a place to the other. Okay. So this is my main function. So I'm going to call the main function here, and depending on the option that I pick, I'm going to go for a place of the order. That's the only thing that I want to explain before going for the collaborative randomness, okay? It's now a CLI. I can pick this option. If I pick option 2, option 1 is going to call one of those functions. Okay, so toss a coin, option 2, it's going to execute that and finish. Now finally tails 1. First thing 4. Okay. Nothing about randomness, it's just about organizing that script. Okay. So if you want to revisit your past exercise, your past homeworks, or even for your final project, this kind of script is very useful when you want to do like project setup. You create a project that anyone can mint their own NFTs, for example, and then you can have a CLI like this. Who is going to be the owner? Who is going to be the minter? How many you want to mint? What is the URL for the URI? And now you can ask those questions in the CLI. Then at the end, you hit enter and then do the whole operation. So you can skip even the interface part for that. Okay, so I'm going to use that for explaining this lesson too, but it's interesting that you know how to use this read line for you to make those CLIs in the future if you want. Okay, I'm going to use these CLI for understanding signatures. Actually, this is not a review. We did not see that on the lesson 14. We had actually we signed a message, but we did not verify that message as far as I recall. Remember, we used a method to sign a message in the front end on the lesson 14. Would pick a private key and sign the same thing Arta was mentioning a while ago. I'm going to do that using these scripts for collaborating on randomness, okay? Coming back for this, collaborative pseudo-random number generation. Before going for rundown, let's understand how we can collaborate on-chain. For example, the commit and review scheme, how we can get different people to properly put information on-chain in a game. I'm going to get to this content just in a while. So rundown is a way for you to do pseudo-random number generation by having a lot of people in a phase of collecting signatures and then revealing signatures and all. So before we get to that complex explanation, let's understand how I can get two people to interact on-chain without, and everything that we put on-chain is public, right? So without having information asymmetry. Let's say we have two people playing paper, rock, scissors on rock, scissors, paper, rock, scissors, yes, on chain, like Alice and Bob. Alice and Bob are playing this game on chain, and Alice plays paper on chain, and Bob wants to win. If Alice has committed paper, it would be that simple for Bob to know that he should pick scissors, right? It would win against paper. So it doesn't make sense to play these kind of games on chain, since every action is revealed. Whomever plays first would have a huge disadvantage because of information asymmetry, right? In a commit and review scheme, you solve that by first committing your play. Instead of revealing it in a public way, Alice would commit a hash 0x185f8 that can be calculated by a hash of paper plus a random salt that she's going to pick. And she's not going to reveal that random salt. She's just going to pick a number. Can be 42, can be any number she wants. And then Bob is going to look, Alice played 0x185f8. I don't know her salt. So I don't know what she picked. She could have picked paper, she could have picked rock, she could have picked scissor. I don't know. So I'm going to take my guess. I think she chose scissor. So I'm going to play rock because I want to win. So Bob is going to pick the hash of rock plus another salt, can be another random number like 0 or 100, whatever number he wants. And he's going to commit his hash to 0x5d403. That would end the commit phase. No one knows what's the result. No one knows how to calculate this game now. We could apply all the techniques like zero knowledge, fully homomorphic encryption, blah, blah, blah in the future. But for now, in this very simple commit phase, at this point, no one knows. We just have the hashes, okay? There is no way for coming back from the hash to the content. I can only go from the content to the hash. So after the commit phase finishes, I'm going to start a new phase called review phase, where Alice is going to go there and is going to review. Oh, I picked paper and I can prove because the hash of paper plus this salt that I used is this. And then she proves, oh, I played paper. 185F8 is exactly what I committed before, so the play is accepted. Alice revealed her play. Now Bob wants to cheat. Oh no, I'm going to lose. If I reveal that I picked rock, I'm going to lose. So I'm going to say that I picked scissors. And my salt was 100, or was whatever salt that I want. And then the hash is not going to collide. It's not going to be the same because the hash of scissors plus this salt is going to be different from the hash of rock plus this salt. And I could be trying all the different salts here for years, decades, centuries, millennia, and the probability of having a colliding hash is almost zero. So Bob has no way of cheating, of trying to pick another combination that would eventually make him to win this game. This is the committee review. The only way for him to proceed is to pass the hash of scissors plus salt, of rock plus salt that he did before, that he committed before, and admit, yes, I lost this game. I picked rock. Or he can just forfeit, he can just not play, and whatever, Alice is going to win regardless. Okay. Is that clear? This committee review scheme is clear for everyone? Yes, Corrado?
Yeah, and just to organize the the game in my head, you have two transactions. The first is the commit phase. You have to sign the transaction, and then you have another sign a message to review the phase.
Yes, right now
Yeah.
I'm explaining committee review even outside of blockchain. You could do that in whatever environment. But if you do with blockchain, I'm going to suggest using signatures instead of hashes, because then you can prove that you signed it. I'm going to do that explanation in the next step. For now, it's just with hashes, without signatures, but it's the same. You got it correctly.
Okay,
You can
but the
see where I'm
salt
going.
can be different. It must be different, the Alice from the Bob.
They can even
So
pick the same salt. It would work.
Yeah.
If Alice picked the salt of 1, 2, 3, and Bob picks the salt of 1, 2, 3, both would work. It's just out of
Yeah.
luck. The salt is
Okay.
picked by the user. The problem is when you forget which salt you use it, and then you em português você tá no sal. Then
Yeah.
you don't have you
No
don't have
exit. Yeah.
you would try to recover. It's very difficult. So you need to keep offline, off-chain with you, which salt that you use it for being able to review later. So it's common for people to use rememberable salts or salts that they can derive from their own account, but they know how to get this salt. Okay. Good. Look at your cameras. A lot of people with camera closed today. Dante, all good. Arda, having some snacks, that's good. Nathan, that was good. Okay, good. Gregory, Marco. Okay. So we're going to use something similar. Like Conrado said, we could use the signatures. I'm going to go very slowly here because we did not see verification of signatures in the past. I guess I mentioned that you could pass the signature from the front end and then verify that signature in the back end as a sort of check, of authentication check, but I guess we did not dwell too much on that. I just mentioned very briefly. So today, let's give a look on verifying signatures first, okay? I'm going to create a pseudo-random.sol, and it is a very complex smart contract. So don't worry about these functions. We are going to see more of them next week. That is like assembly stuff here. Yeah, you're going to see that next week, okay? So don't worry about that. Let's create that pseudo random.sol. Where we're going to use collaborative random number generation. Put the space in the beginning. Yes, it's bad. Pseudo random number generation. I'm going to copy all of this code. You can ignore that ugly part of the code. I'm going to show how to get this verified signature later where I'm getting this. So don't worry, I'm going to explain assembly. I'm going to explain assembly. I'm going to explain what is this assembly block, very highlight, but you don't need to worry with that. Our scheme here is this. Whenever I'm getting a random number, I'm going to have a seed being passed by call data. So minting the NFT, playing that game, getting the lottery, and now I'm going to get the random number by passing a seed, and this seed is going to be used to calculate the random number. But then you can say, oh, this is dumb because I can try different seeds, and then I can pick whatever seed that leads to a better result for me, leads to a scenario where I'm winning that lottery. Wait, there is a catch. Before using that seed as a entropy for getting the random number, I'm going to check if this seed that I passed is exactly the seed that I have committed before. I'm going to verify first one person that have signed before I have a function to set signature. So I need to verify if that person have set that seed correctly. So it's kind of a commit review. First, I'm going to pick a seed, but I'm not going to review the seed that I picked. Like, think on a random number, but don't tell me. And instead of committing this random number, you are going to sign, which is set signature, and you're going to sign. My random number is this. But there is no way for going from the signature directly to the random number. You just sign. Okay, I thought on a number, and the signature of this number is like that. And when you pass the seed, you need to verify that this number that you passed is exactly the same number as you thought before. Let me show that with the script first. I have this get randomnumber.ts, and I'm going to do this to the those three methods now: message signature, random from a sealed seed, and random from a block hash plus a sealed seed. I'm going to do the operations 3, 4, and 5. So operation 3, I need those two scripts: signature and test signature. Let me copy those two first. For the operation 3, I'm going to have a function to sign something and another function to test that signature. Okay, it seems that they changed the method of hex to signature something else, but I guess it's going to work. Okay, tested that a few months ago, 2 months ago, so it should work. So when I pick the option 3, I'm going to go for the function of signature, for testing a signature. And this function is going to get my first wallet, is going to ask a message to be signed, and I'm going to type a message. My random number is 42, or hello, my name is Mateus. I'm going to sign a message here. I'm going to pass a string, and I'm going to call this sign message method. Okay, I guess I have it here in the reference. Sign message, yes. So this is going to pick my private key, and it's going to sign that message. It is using the EIP 191 format, so there is no way to calculate my private key back or to force money to be sent for someone else, because this is not going to be a valid RLP. Okay, the same things that Arda was saying before. If you try to sign a message raw by yourself, applying cryptography, you might do some mistakes and you might review a private key. So using this method, sign message, is going to use this EIP 191, which is safe. We're going to see that next Monday. Very briefly, like 5 minutes, but we're going to see that. So we can call this a sign message, and the message is something like hello world and whatever. It is going to give me a signature like that. There is no way for going back from signature to message. But having the signature in the message, I can check who signed it. Or having the signature, the message and the address, I can have the signature. Those two are interchangeable. See, I'm going to show that very slowly before we use that for randomness. I have half an hour, so it's good enough. So I'm picking this message that came from the terminal, and I'm going to sign this message to have a signature. Okay, and then I'm going to pick the members of that signature later, the members of V, R, and S. We're going to set the signature in the smart contract so that it can be used later for getting the random number. Let me explain one thing about those signatures first, okay? Because we're going to use the elliptic curve signature, elliptic curve digital signature, ECDSA, elliptic curve, forgot the name, sorry. ECDSA, I should remember this name, beg your pardon for that. Come on, in English. Elliptic curve digital signature algorithm. Yes, I forgot the word algorithm. ECDSA. Since we are using ECDSA for in those curves, for every point that you pass, you are going to have an answer. Okay. So when using this signature here, I'm going to do that very slowly before we use that for randomness. Let's just test the signature, sign things and test the signatures so that we understand that this relationship between the message, the signer, and the signature. And we're going to see that with different messages for the same signer, we have different signatures, but also with different addresses, for different signatures for the same address, we can have different messages. We're going to see that. Okay. Question, Dante, before we get there?
Yeah. Do you install the Open Zeppelin dependencies
For the smart
for using
contract,
that
yes.
import?
For the smart contract, yes. I have copied the package.json where we have this. So this is why it's working for me. I'm picking even random words, which we don't need. So I've been copying the package.json from previous lessons, from yesterday's lesson. So we inherit all of those dependencies that we have installed.
Thank you.
Okay. But for this signature, we are not going to use OpenZeppelin. I'm going to use sign message from VM. Okay, this method that I have here. Let me show how it works. Let me pick the option 3. Option 3, message signature. And then assigning a message with the account of address 0xF39F. This is the account 0, the default account from Red Hat runtime environment, right? Using VM. And then I'm going to enter a message beside it. Right? This can be any message. It can be any string that you want of any length. And when I pass this message, I'm going to use the private key of that account to sign this message plus this in the beginning, this hash, you know, so it's going to be safe. I can probably review that signature without any risks of leaking my private key here with this assigned message. And the signature computed from this was that 0x6308349. So if I verify the signature to recover the message address, passing the message and the signature, if I pass this message that I sent plus the signature, this function recover message address can calculate what was the address that signed this. So if I pass the same message signature, this, and with this message, any message, this is going to work. This message signature matches with the address 0xF93FD, blah, blah, blah. This is the address that we use it, right? But now let me show you something interesting. If I say that I signed this signature, the same signature, with another message, like something else, my message would be any message, right? This is string. But now I'm passing something else. I don't have any error. Weird. It doesn't give me an error. I've changed the message to something else, and I've used the same signature. Because I'm using elliptic curve digital signature algorithms, this is going to have a result. This is a function, mathematical function. So this is going to have a result. Arda, you should know that even much better than I do. I studied that on the surface. This is going to have a result, a mathematical result, regardless of the input that I pass. So by coincidence, with a lot of air quotes here, if this person 0xB0F4D2 signs the message something else, by coincidence, it's going to have the same signature as my address signing the message, any message. You see? This is by design. This is mathematics, cryptography. And if I alter the signature, let's say I'm going to pick the same signature as I have here, and I'm going to change a little byte. From 0 here, I'm going to change to 1. From the 0 that I had, 50 or 0F, I don't know, I would change from 51 or 1F. We need to see where the byte starts here. So changing a very small change. And the message is the same, like any message. So by coincidence, again, this other address, when signing the string any message, would have a signature that is very, 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 very similar to mine. Just one little difference, one number, one hexadecimal number different, okay? Is this clear? How this signature would work? Make sense? Yes, Browns?
Okay, so my question is, why are we using Ketchup 256 or SHA 256? Ketchup
No,
256
here
or SHA.
we're using signatures. So in the example of commit review that I used it a while ago, we were using hashes, yes, but here we are using signatures. Okay.
Okay, okay.
The same
Thank you.
signatures we used it on lesson 15 or 14, actually 14. And there are these kind of signatures here. You can use a private key to sign any data, but you can make sure that it's not going to be a valid RLP because of the way that this signature is structured. Okay.
Yes, thank you.
So now that I can prove that I was the provider of that signature, now I can implement those other two functions. Seal seed and combined seal seed, random seal seed. Let me put those two here and let me add them to the main function. Seal seed and combined. Oh, actually, what was the name? Random seal seed. Let me put those two. Because I have some problems with those script. What's happening? See. Oh, I pasted it wrong. My bad. Sorry about that. Because I did something wrong here. Yes. Now it seems that is correct. I have seal seed, I have random seal seed, I have test signature, and I have signature. Okay. Now I want those both here and here. Okay, sorry about that. So I'm going to pick option 4 first for us to understand how that smart contract would have collaboration of first one person signing a message and then storing that message inside the smart contract, setting this signature there inside the smart contract. And then in the future, let's say after a week or after 10,000 blocks or something like that, I'm going to get that random number. Imagine the flow like this. On Monday, I set a signature number, and the seed of randomness that I thought is the number 4269. And on Friday, I'm going to roll that lottery or that random number, and I'm going to use this seed that I use. If I try to pass a different number, if I go there on the Friday and see, oh no, this number that I passed before is not good, I'm not going to win, I'm going to try and pass another number, I would need to find some sort of collision, almost impossible, that signing another number would give me the same signatures. Possible to do that. Very, very difficult, if not impossible, to forward that. So it would deny me. I need to stick to the same number that I used before. So here I have the collaboration between two members, the person providing the seed and the person using the randomness in the future. It's a collaboration of two. So I'm going to first call the set signature here on the line 118 with the signature that I passed. And then later, when trying to get the random number, I can try it correctly in the line 180, I set the signature 183. I get the random number using the correct seed. and 187, I get a random number without the correct seed. Okay, let me do this operation. Number 4. So I'm going to deploy the contract. I'm going to set a random seed beside it. So let's say I'm going to use potato as the random seed. That's going to be my randomness number. So the sign message is this: 0xAE17, blah, blah, blah. So when I try to get the random number with the original seed, I have this random number. When I try to get this random number without the original seed, I have this operation failed. Okay, so it was checked correctly. So I have this collaboration of those two parts. It is true that the person giving the seed is now the only person controlling the result. So I could bias the result in my direction, in my favor, so that I can win this lottery or this game, whatever. This is true. But at any time now you can combine the randomness of the person that passed that seed with, for example, the block hash, or with an oracle, or the block hash and the oracle. You see, now you can collaborate with a lot of randomness. And unless that person that signed it is the block producer at that time, which is very unlikely, you're going to have a good number generation. Because when I'm passing that seed on Monday in the past, and then I'm going to use that seed after cliff period in the Friday, I have no clue of what's going to be the block hash at that time. I don't know what's going to happen in the future, right? So the amount of bias that I can do is very, very limited here. So get combined at random number. So let me show that first. Let me do the operation 4 again. So this was the number, a random number that we got, right? So I'm going to pass the same signature again. I'm going to get the same random number. This was the random number that I did. I'm going to do operation 4 again. And I'm going to pass the same seed, potato. I don't remember if I did a capital P or not. I guess I did. Let me do number 4. Potato. And this is the same random number. So it's deterministic. Whatever I do as a seed is going to make the random number, right? Now, if I combine both, operation number 5, if I combine random entropy from the block hash plus the seed, I did something wrong. So if I combine a random, the two randomness sources, the same source, the potato, with the seed, I will have a totally different random number now. This one. And if I do that again with the same seed, I'm going to do the operation 5 again. A totally different number. See, now I can have the combination of those two factors. Okay. Questions here about this design before we go for the rundown? So here, Ivan, I'm just doing the example of how we can collaborate. This is not the best design yet. It's just showing how different people can collaborate using this solution for information asymmetry so that they can bias a little the results, a little of bias per each. Okay, so this is the explanation. And we're going to see rundown, how it combines all of that. Rundown is an implementation, has been there for like a decade or so, running as a DAO architecture, as a DAO proposal that people could interact there. collecting valid bytes of information. Each member of this DAO would give a little a contribution at a specified period, at a epoch, at each 6 blocks or something. And then I would collect all of those contributions, all of those individual biases to calculate a random number. And then I would give some token economic incentives for these people to participate. Okay. So each of those members participating in this transaction, participating in this contribution for the random number, they would give a little information, little bias. They would nudge the random number in a different direction. This at the end would give us a single number. We pick the reference here. This would give us a single number. Pick the reference link. Since the EIP 4399, so that is the version 0.18, we have, let me go for it again. We have in all of the blocks post the merger, we have this review, where I have that in the consensus information. We have this review of block randomness included in the beacon chain of a canonical version of Rundown, giving this collaborative randomness from all of the participants. Here we are using the block producers. So Ivan, the same thing that you mentioned a while ago, at each epoch, I would have the list of block producers that would nudge, that would give a little contribution on this block randomness, giving a little bytes. If we apply a good enough cliff period, this is safe enough for us to have a good random number generation with almost zero impact, almost zero control at the end of an individual person to the overall number. Unless a person is the block producer for the whole period of the cliff period, that is extremely unlikely, they are not going to influence this randomness. They are not going to have any control at all of the random number used there. And since the number, the EIP 4399, you can use this pre-rundown review as the opcode, the same opcode that was difficulty before. It's now supplanted for pre-rundown. We can use it since the version 0.18 of Solidity, okay, in the EVM versions of Paris or above, okay. And they can impact the bias by, they have some operation like you flip, imagine a collection of cards, a pack of cards. You have the option of flipping the list or no at each block. If you don't flip the list, you don't have the block you want at the end, which is kind of bad, okay. And are like using those mechanisms here, we're going to see next Monday using the ERC 191 and all. This is safe, okay? You're not going to reveal your private key or anything like that. Okay, this is protecting your private key. It's not going to be a valid RLP, no matter what you do. So if you follow this path, there is no way for you to mess up unless you do anything else around it. But if you follow this path, there is no much big deal. And the amount of randomness, of entropy that you have here in the pre-rundown, it is way higher than what you have in the block hash, because it's collaborative between many players. It's not possible to have one single player with more than, let's say, 1% or 0.1% of control of all of the bias of this. It is the pre-rundown, the previous rundown review. So it is for this last block, it is reviewed for more than 4 seconds or so because of the block time. But if you implement a cliff period, it's good. You have enough protection against manipulation here. And to implement is very quick and easy. We can do that in way less than 5 minutes. We can implement this random.sol with this Solidity code. Random.sol like this. It's going to use the block prev rundown. This is only possible after the Solidity 0.18. So if you try with all the Solidity versions, you're going to have an error. If you try with newer Solidity versions, you're going to have it working. You can tweak the hard configs if you want to test that out. Right? Do you like this? Your contract is not going to work. Do you like that? Your contract will work. Okay, very, very easy to check. And then we're going to test with this script, this rundown. Okay, for testing the random number generation from this smart contract. Last but not least, using this rundown function. Before the other ones, let me do the rundown here. Okay. Let me run this option number 6. So using the EVM version of Paris or above, this difficulty method, this block difficulty, is going to get the randomness not from the actual difficulty from the blockchain, because since the merge it's 0, we don't have proof of work anymore, just proof of stake. And then the random number can be calculated from the previous rundown review. Right now it is a review that was public for 4 seconds, but if you use that in the future, you, like we did in this previous example of the random hash, the plus a CLC. If you do that in the past, you log that time in the past and you use a review of the future, any validator would have just 1 byte of bias per time. They can't bias the whole result unless they manage to be the block producer every time, which is insanely difficult. And if someone gets 1 block producer to break this combo just by 1 block, their randomness is going to be completely messed up. It's going to be completely resetted, and they are going to have 0 power to bias the whole decision at the end. Okay. And Arda, it's not guessing the random number. Okay, don't know if I explained that in the past explanation. There is no guessing the random number here. The random number is calculated by the block properties that we have at the time. Okay, and the validator is proposing the block. The SHA hash is calculated from the block contents itself. It can manipulate what it's included in the block, the transaction lists, when it's going to submit the block, yes and no, but it's not going to guess a random number or pick a random number to include as an intrinsic information. Okay. Speaking of including a random number as an intrinsic information, we have the Oracle pattern. Yes, this one that I mentioned last Thursday, where you can ask a random person outside of the blockchain to provide you this information. There are some brilliant implementations like this. I even mentioned here in the README. For example, the oracles from Chainlink, for example, that you have verifiable random functions. So you ask for the oracle, hey, give me the hash of the future block number. And then they would calculate that at the time, and they would give it back for your smart contract. There is no way to tamper with the verifiable random number because the function is exact, is defined. It's just that it's depending on a variable that is going to be used in the future. What could happen is that the Oracle network can fail. It's not Byzantine fault tolerant. It can fail. They can have a delay, or they can submit a wrong information to be slashed later and all. And this would cause risks coming from the Oracle network. The thing is that the risks of this happening even for millions of dollars, sometimes billions of dollars worth of transactions, is almost zero. Oracle networks like UMA, like Chainlink, even the Teller one that we saw, they have this resilience against fake information, especially verifiable information like VRF. And then there is whole discussion, should we use Rundown or should we use VRF? Well, we can use both. For having a VRF number from an Oracle network, you need to pay. You would need to pay the Oracle network for them to work for you. You would need use some pre-funded fee. For using the Rundown, it's already there. You don't need to pay anything extra. In the best scenario, you compare both. You have the randomness from the Rundown, and you have the randomness from the Oracle, using both. And then you can have very, very, very secure random number generation in your smart contract. Okay. And that's it. This is the explanation about randomness. Tomorrow we are going to use that for building a small challenge of a lottery. And we close the week with a fun weekend project for you to test your skills, for you to prepare for the final project in a few weeks. Okay. And that's it. Thank you, everyone. I hope you have enjoyed today's lesson. See you tomorrow for more. Bye-bye.